So in this lecture, we used some very basic notions from Honors Linear Algebra 1, which is direct sums and the property that complex operators always have an eigenvalue. And we use very much some of the things we saw in lecture 12. First, that if we take powers, larger and larger powers of an operator, then the kernel increases. And also that if we take an operator, raise it to the highest power, which means the dimension of v, then the v can be decomposed as direct sum of the kernel of this power and the range of this power. And we defined what is the generalized eigenspace, and we saw that they are linearly independent, meaning generalized eigenvectors corresponding to distinct eigenvalues would be linearly independent. Then in the lecture of today, following on this notion of kernels that are inside other kernels, we define what is the notion of a nilpotent operator. A nilpotent operator is the one that some power of it gives you the zero operator. And then we saw that if an operator is nilpotent, regardless of the field, there is a representation where it is upper triangular with even zeros on the diagonals. Then we introduced algebraic multiplicity as simply the dimension of this space. This would be the algebraic multiplicity of a generalized eigenspace. And then we saw that this space, it is actually invariant under the operator t, this operator t, it is invariant. And if we restrict the operator to this space and subtract the identity, or of course lambda times the identity, this operator on that subspace is nilpotent. So it starts to give some motivation of why we care about nilpotent operator. And then this is the reason. And we finally saw this decomposition, which works on only when the field is the field of complex numbers, which says these subspaces, the generalized eigenspaces, they completely decompose our vector space. And now from there, combining all these three, the properties of nilpotents having matrix like this, the fact that each of these subspaces is invariant and that t minus lambda I is nilpotent, and the fact that these subspaces span the entire vector space, we concluded by showing that every complex operator can be put in a form where it is block diagonals and each block is upper triangular, and of course with the respective eigenvalue on the diagonal. So here these arrows, they illustrate where each of these definitions or properties were used in today's lecture. So here I'm showing explicitly these connections with previous material, including the material of Honors Linear Algebra 1 and the material of lecture 12. As pointed out by many students, there's not much connection between this topic and the topic of inner product spaces. In fact, there's no more inner product in this part of the course. We're just talking about vector spaces and operators on these spaces. Now, I would like to make some comments following on what many students wrote in the exit ticket that was requested from students after the lecture. So some students pointed out that the lecture explored very much the notion of kernel and range of some operators. I think this is true, but it appeared more as a auxiliary result, which is one of the main results of lecture 12 that we have used here very much and here. And other than that, this is not the main point of the lecture. I would say the main point of the lecture are this notion here of algebraic multiplicity, the fact that by this decomposition, the sum of algebraic multiplicities equal the dimension of the space, the fact that these generalized eigenspaces are invariant and the restriction is nilpotent, and what you get as a product of all of these that block diagonal with upper triangular blocks. Some other students mentioned that well, block diagonal is better than diagonal. And well, for that we need to understand what's the meaning of better. I would agree it's better because, well, that's all we can have. We have block diagonal, and as we know, not every operator can be put in diagonal form. So it's better in the sense that it's more general. But on the other hand, if you get pure diagonal, that means block diagonal with the blocks all being one by one, then I would say pure diagonal would be better if that is possible at all. And some students mentioned the notion of geometric multiplicity. I'm not sure that appeared in the textbook at this point, but well, we all know that geometric multiplicity is just of an eigenvalue, is the dimension of the eigenspace, and that is bounded from above by the dimension of the generalized eigenspace, which is what we call multiplicity, or algebraic multiplicity. Some other students, they mentioned that all this notion of finding generalized eigenspaces instead of eigenspaces, it solves the issue that, well, not always it is possible to get such a decomposition with the eigenspaces here. So I would agree it solves the issue in the sense that it does the best we can. It's not so beautiful to have the space decomposed like this, to have a matrix which is block diagonal instead of diagonal, but that's life, that's the best we can get. Other students, they pointed out, and I found it very interesting, that the idea of this decomposition, and to prove it using induction, induction on the dimension, it resembled a lot the proof we made for the spectral theorem. And another student pointed out that this decomposition, it resembles also, it feels similar to the notion of projection and orthogonal complement. They feel like similar objects or objects that try to accomplish similar tasks. And that's all for now. I think this gives us a very good closure for our lecture 13.